Welcome back, and welcome to section 3. In this section, we're going to take a look at how we can build a scalable data warehouse using Amazon Redshift. So first of all, we'll make a start by having an introduction to Amazon Redshift, and particularly what it is and how it differs from a traditional database, such as what we've been looking at with Amazon RDS in the previous section. Once we have that understanding, we'll go ahead and dive into the Amazon console and create an Amazon Redshift cluster and look at how we can actually connect to it and start working with it. Next, we'll look at a typical data warehousing use case pattern where we have to load data from a traditional operational system running on RDS into our Redshift data warehouse. And finally, we'll take a look at how we can load flat files using Amazon S3, again, into our Redshift data warehouse. In this video, we're going to take a look at Redshift from an introductory point of view and get an understanding of what it is, how it works, how to use it, and most importantly, how it differs from a traditional relational database. So Amazon Redshift is a very fast, very scalable, fully managed data warehouse on the AWS cloud. It's a cost-effective way to analyze all of your data using standard SQL. And one of the nice things about Redshift, and perhaps one of the most powerful features about it, is that you can connect it right into your existing business intelligence tools. So if you're used to using things like ClickView and Tableau against your on-premise data warehouse, you can continue to do this using Amazon Redshift. And really the power of Amazon Redshift comes from its capability to run high-performance analytics queries against up to petabytes of structured data using standard SQL language. And Redshift features a number of sophisticated query optimizers, as well as high-performance columnar storage and local disks in order to accelerate massively parallel query execution. So Redshift is actually based on Postgres, and that's the same Postgres that we launched in the previous section using RDS, but with a number of modifications. Notably, then Redshift now uses a columnar storage model as opposed to a tabular storage model, and it also adds the ability to scale out a database horizontally. So you can add multiple compute nodes to your cluster in order to scale data processing in a massively parallel way. And in order to do this, unfortunately, we lose some of the functionality we get with a traditional database. So one of the most important things to bear in mind when considering Redshift is that it really is designed for data warehousing operations and not for database operations. And this means that we lose a couple of important features. Notably, the ability to define primary keys and the ability to define a transaction. So Redshift doesn't feature either of these things. They simply don't exist as a concept. However, you can continue to communicate with client applications using industry standard Postgres, JDBC, and ODBC drivers, which means it will work with any application that works with a normal conventional database. And like I mentioned before, Redshift is a cluster-based computing environment, so a cluster is composed of one or more compute nodes. If a cluster is provisioned with 2 or more compute nodes, an additional leader node is used to coordinate the compute nodes, and this handles all external communication. So typically an app will communicate with the leader node only, but work is distributed evenly across the cluster by that leader node. So again, the important difference here between Redshift and a more standard database is this massively parallel processing execution model. And this allows it to perform much faster execution of very complicated queries on huge amounts of data that you simply wouldn't be able to do with a traditional database. So with Redshift, multiple compute nodes handle all query processing, resulting in the final aggregation of your data. And now if we think about a traditional BI type query, typically we're doing scans across the entire data set across a fairly restricted number of columns, and this is well suited to the massively parallel processing model leveraged by Redshift. And each core of each node executes the same compiled query on its own portion of the data set. So with Redshift, your data is actually split across the entire cluster, and local compute nodes work on the data partitions or the data segments that are stored on their local nodes. And loading data from flat files takes advantage of massively parallel processing by spreading the workload across these multiple nodes and at the same time reading from multiple files. So not only do you get to leverage multiple cores across multiple nodes, you also get to leverage improved disk performance because you're reading from multiple file systems on multiple nodes all at the same time. And again, one of the key differentiators of Redshift compared to a traditional relational database system is that it leverages columnar data storage. So columnar data storage is much more efficient when performing traditional BI type aggregation queries. And if we think about what one of these queries might look like, normally it's a select statement that only actually selects a small subset of the columns in a table and then performs some kind of aggregation on them. Now, what that means is the database engine has to scan the entire table in order to compute the aggregate. And because of the way the data is actually structured on the disk, that means the database engine actually has to load all the data for every row in the entire table. With columnar data storage, the database engine can actually only load the data for the column that's selected versus having to load all of the data from the entire row. So it results in massively improved performance when performing these BI type aggregation queries. So of course this reduces the number of disk I/O requests and reduces the amount of data that's being loaded from disk. And loading less data means more data can be processed in memory when executing queries. So Redshift is really optimized for data warehousing and for BI type business intelligence, data warehousing, data analytics type queries. It's petascale. We can add as many nodes as we want and scale out horizontally, and the performance improves horizontally as we scale. You only pay for what you use, exactly the same as with other Amazon AWS resources. It's fault tolerant, as you'd expect from a cloud service, and backups are made automatically to Amazon S3 using the snapshot model. And of course, we can then restore from snapshots when we need to. You can configure encryption, both in transit using SSL and at rest if you require. And Redshift can either take care of the key management for you, or you can manage your own keys using Cloud HSM or Amazon's key management system. As with every other AWS resource, you have complete control over network isolation. You can specify security group rules to control network access, and you can of course also place your Redshift cluster in a private subnet. And in terms of audit and compliance, Redshift integrates with the standard AWS tooling. So that's CloudTrail, CloudWatch, etc. And you can then use that to keep a log of all SQL queries that are performed against any of your Redshift tables and download them into S3. Redshift also features data compression. So you can compress your data on the disk, which of course will then reduce not only storage requirements, but typically also improves query performance. Now, one of the things we find in the data warehousing space is that disk I/O is commonly a bottleneck for query performance. So we've reached the point in today's computer systems where the CPUs are more than powerful enough in relation to disk performance to handle highly compressed data. So actually, although maybe 10 or 15 years ago, when CPUs weren't anywhere near as fast as they are today, storing a compressed file on the file system would be slower due to the time taken to decompress it. Actually today, CPUs are so heavily optimized for these type of queries and these type of decompression operations, it's very, very advantageous for us to store our data in a compressed format on disk. So if we do that, when a query is executed, the compressed data is read into memory and then decompressed during query execution. And this is much, much faster than storing raw data on the disk decompressed. And again, data is stored in a columnar fashion. So similar data is stored sequentially, and Redshift is able to apply adaptive compression encoding specifically linked to the column data types and the column data that's requested in the query. Redshift also features a very advanced query optimizer. So the way this works is the Redshift execution engine contains a query optimizer that's massively parallel processing aware and also aware of the columnar-oriented data storage method that Redshift uses. And this allows specialized processing of complex analytic queries that regularly include aggregation, lots of joins, and even subqueries. So the way this works in a multi-node cluster is that the leader node distributes fully optimized compiled code across all nodes of a cluster. So when your application connects to a Redshift cluster, it's connecting to the leader node. And when that application submits a SQL query, the leader node will optimize that SQL query and compile it into executable code for all of the worker nodes. That code is then distributed across the cluster and executed on those worker nodes. And as you'd expect with any modern database engine, the compiled code is cached across sessions, so if you execute a similar query with different parameters, there's no need to recompile the SQL code. And the execution engine compiles different code for the JDBC connection protocol and for the ODBC connection protocol, so two clients using different protocols will each incur the first-time cost of compiling the code. So do bear this in mind. If you're expecting queries to be cached across JDBC and ODBC sessions, they won't be. Currently at present, Redshift only supports single availability zone deployments. So do bear this in mind if you're considering using Redshift as a production system or a production part of your stack. Because this does mean if an availability zone becomes unavailable, you'll be unable to use your cluster until power and network access to that AZ are restored. You can run data warehouse clusters in multiple AZs by loading data into two Redshift clusters in separate AZs from the same set of input files, but then of course you'll have to manage this yourself. Another option is to use a new feature called Redshift Spectrum, something we're going to be exploring in the next section, where you can spin up multiple clusters across AZs and access data in Amazon S3 without actually having to load the data into your cluster at all. And this is really where Amazon are going with the next generation of data processing, an environment where you don't need to even think about the servers that are supporting your application or your use case. And again, we'll explore that a little bit more in the next section. In addition, you can also restore a data warehouse cluster to a different availability zone. So for example, if your availability zone or the availability zone in which your Redshift cluster is running has gone down, as long as you have a recent snapshot, you can just restore to a new cluster. So what's a typical design pattern for using Redshift or a data warehouse? Well, typically the way it's going to work is you'll have multiple application databases or operational systems, and these are the real-time systems that your users and your front-end applications are connecting to. So your transactional systems, your application DBs, your CRMs, any other data systems in your enterprise that are mission critical. Those remain unaffected. Typically you then have an ETL layer, and that stands for extract, transform and load. And you'll normally do an incremental load from each of these production systems on a regular basis. That may be hourly, it may be daily, it may be weekly, depending on your use case. But you'll take an incremental dump of data from these application databases and then load it into your data warehouse. And there may be a transform step here as well to clean the data if required. And then the result is this single massive database that contains multiple schemas, multiple databases inside it that may include metadata, summary data that's pre-computed as part of the ETL process, and commonly also the raw data. And this is a really key point. The idea of a scalable data warehouse is that you can store all the raw data across your entire enterprise in one place and process it ad hoc when you need to. And typically this is such a large volume of data that it simply couldn't live in any of these databases, either due to technical limitations or purely the fact that you'd end up slowing your production systems down. And then finally, you can connect your traditional BI tools up to them. Things like Tableau, things like ClickView, even Excel. You can run queries with Redshift and export the data to CSV files, which you can then open and manipulate and slice and dice with things like Excel. So that's everything I wanted to talk about in this video.